Hi guys, welcome to another lecture on organic chemistry 2, and today we're going to be talking about infrared spectroscopy, or IR spectroscopy for short. Well, what is IR spectroscopy? Well, it's the measurement of the absorption of electromagnetic radiation, and you might see just EMR throughout this lecture in the IR range by compounds placed in the path of a beam of IR radiation. So they measure the absorption of the radiation in the IR range, right? So a molecule is not a rigid assembly of atoms. I would like you to think of a molecule like a ball and spring, right? So a popular analogy is a system of balls of varying masses, and the balls represent the atoms, and they're connected by springs of varying lengths, and these springs we would represent chemical bonds, right? So we know what a spring is. A spring will be moving in and out, and that is how I want you to think of molecules, as vibrating and not rigid. So the usefulness of the ball and spring model is limited, but this model is very relevant to IR spectroscopy. It indicates that there's always some vibrational motion associated with a molecule. So nonlinear molecules, and the one that we can readily think of is water, with n atoms, and water would have 3 atoms with 2 hydrogens and an oxygen, have 3n minus 6 fundamental modes of vibration. So here you may not really understand what fundamental modes of vibration mean, but we can do that calculation. So 3 times 3 gives us 9 minus 6 would be equal to 3. So a molecule like water, a nonlinear molecule like water, would have 3 fundamental modes of vibration. So what is the process of infrared absorption? Well, as a molecule vibrates, as we can think of a molecule as balls and springs, so as it vibrates, it actually gives rise to an oscillating dipole moment. So what is a dipole moment? Well, a molecule that is polar would have different atoms of varying electronegativities, right? So we'd call this molecule polar. And in the presence of an electrical field, it will turn to align, right? Much like the image that we have here to the right of our screen. We see where we have a polar molecule represented by these green and is that purple or pink plus, right? So plus and minus, so that represents a polar molecule, and in the presence of an electrical field it will turn to align. So notice that the negative side of the molecule aligns with the positive, and the negative aligns with the positive on this side, right? So the frequencies of molecular vibrations coincide with frequencies in the IR region of the electromagnetic spectrum. And so absorption of IR radiation occurs when the oscillating dipole moment of the molecule interacts with the oscillating electrical vector of the EMR, right? So we just want to think of the molecule vibrating, giving rise to that dipole moment, and we want to imagine the molecule coinciding with a particular frequencies in the IR region of the electromagnetic spectrum, and the absorption of the IR radiation occurs when the oscillating dipole moment of the molecule interacts with this radiation, right? So we might get the gist of what is happening here, but let's see if this video will further clear that up. All right, so hopefully that video would have added some clarity to what I just mentioned and introduce you to some other topics which we are going to cover and um, dive into. So that leads us to our first question, which says, nonlinear molecules with n atoms have how many fundamental modes of vibration? So you have an MCQ here. So is it 3n minus 5, 4, 6, or 7? You have seen it twice so far in the video and on the slide. So what is it? If you answer the 3n minus 6, then you are indeed correct. Now on the video, you were introduced to these vibrations, and I'm sure you may have met them before in your chemistry career. So just to mention again, our stretching and bending vibrations. So there are basically two types of molecular vibrations. They are stretching and bending. These are illustrated for a triatomic fragment. So obviously tri means three, so three atoms in that compound or fragment, sorry. So fragment means that it's part of a molecule, right? So let's look at the stretching vibration first. So we're seeing here the symmetric stretch, and we're seeing our asymmetric stretch here, right? So I have the two images here, two sets of images. They're both saying the same thing. One is an animation and one is not, right? So just to get you familiar with the animated version versus seeing it on a plain paper. So this is our symmetric and asymmetric, and as the name suggests, it suggests the stretching vibration. And for the bending vibrations, we have in plane bending vibrations, and we're seeing here scissoring and rocking, right? So it's in plane, it's in one place. So if we think of it as, just a sheet of paper, and the atoms are all three atoms are aligned on that sheet of paper, the movement is occurring within the plane of that sheet of paper, right? So these are bending vibrations. We have scissoring, and I don't have to explain the movement because you're seeing the movement both in the animation and otherwise. All right, so we have that was in plane bending vibrations. So we have out of plane bending vibrations. And we see here where we have wagging and twisting. So twisting, I'm sure, you would get twisting if you imagine yourself twisting. And then wagging is out of plane because the two blue atoms are moving out. So if we think of for example, the yellow atom in the plane or the paper, then we can think of the blue atoms coming in and out of the paper, right? So these are both out of plane bending vibrations, wagging and twisting. So we did see in the video a bending and stretching vibration there. So this is just further reinforcement. So continuing on the IR absorption process, molecular vibrational frequencies are coincident with IR frequencies, as we saw in the video, right? So this is just further reinforcement. So when a molecule is irradiated with frequency, well, the electromagnetic radiation frequency is equal to the vibration frequency, energy is absorbed as we saw in the video. Absorption of energy causes the amplitude of vibration to increase, and this is called the excited state. And when the molecule reverts from the excited state to the ground state, as we saw, the absorbed energy is released as heat. So this is just adding words to further reinforce what we saw in the video. All right, so that leads us to our next question, which says, what type of vibration is observed here? So based on the movement that we're seeing here, what is that vibration? So without going back, see if you can test yourself to answer this. Well, if you guessed or if you knew wagging, then you are indeed correct. All right, so now we're looking at the range of the IR region and units used. So the IR region of the electromagnetic spectrum, and we looked at it last time, right, in lecture 1, and we looked at the IR region specifically, and that it spans the wavelength of 0.7 to 100 microns, right? So we see some conversion factors here where 1 micron is equal to 10 to the minus 4 centimeters, which is equal to 10 to the minus 6 meters, right? So these are our conversion factors if we need to convert between microns and centimeters and meters. The most analytically useful vibrations, however, occur between 2.5 microns and 16 microns. And so this region is actually called the mid-IR region, where IR absorptions are usually expressed in units which are proportional to frequency and therefore proportional to energy, because we recall this equation here where our frequency is directly proportional to energy. So if our IR absorptions are expressed in units which are proportional to frequency, then clearly there's a direct relationship between frequency and energy. Continuing on the units used in IR spectroscopy, so what we will see, and when you look at your spectrum, you would recall that the unit is wave numbers or reciprocal centimeters. But the one that we will stick to is wave numbers, right? So it's cm, centimeters to the minus 1. So we don't say centimeters to the minus, we just say wave numbers. Right? So when we say wave numbers, this is what we mean, cm minus 1, right? So don't say cm minus 1 or to the minus 1, just say wave numbers. So we stick into wave numbers. The symbol is nu bar, right? So this is the symbol. And you might see I have a tilde here, but it might just be a bar, like a straight line covering the V. And it's the same thing essentially, right? So whether you see a tilde, which is what I have here, or a straight line, we refer to it as nu bar. Nu bar is equal to 1 over wavelength, right? So when wavelength is in centimeters, it's equal to 10 to the 4 divided by the wavelength when wavelength is in microns, right? So think of it this way. So the equation is dependent on the unit of wavelength. So the last time we did we looked at the symbol for wavelength, which is what lambda, which we have here. So depending on the unit for the wavelength, so the wavelength could be in centimeters or microns, the equation will change. So for example, if we have 6.2 microns and we want to convert that to wave numbers, right? We just plug it in this equation because the wavelength that we have is in microns. So 10 to the 4 divided by 6.2 gives us the wave numbers, which is 1613. The mid-IR region is 2.5 to 16 microns, and it becomes, when we do the conversion, 4,000 to 625 wave numbers. Nowadays, the bar sign on our new bar here is commonly omitted, right? So you might not see the tilde or the dash above the V. So when new, and we're going to say new, right? Because it's a Greek alphabet. When new is used in the context of IR spectroscopy, it is understood that the units are wave numbers, right? So anytime we see this symbol here, we say wave numbers. And whether or not we see the bar, we know that once we are in the context of IR spectroscopy, we're talking about wave numbers. So the advantages of using wave numbers is that, well, we have two advantages here. So this conversion here was on the previous slide. We did mention the mid-IR region, what it is. We mentioned these two already. So what are the advantages? Well, 3 and 4 digit numbers are convenient to work with. It's easier to work with 4,000 to 625, right? Versus 2.5 and 16 and even, decimals and all that, right? It's just easier to work with 3 or 4 digit numbers. And then the second advantage is the magnitude of the number is directly proportional to energy. So as we saw, if we know the frequency, there's a direct correlation to energy. So absorptions occurring at high wave numbers are of high energy because of that equation that we mentioned. So that leads us to our next question. Convert the following wavelengths to wave numbers, right? So we have A, 10 microns, and B, 2.5 times 10 to the minus 4 centimeters. So pause, take a second if you have to go back to, or conversion factors here, then do so. All right, so let's look at the answer. All right, so if you plugged in the values in these equations and worked it out, you would have gotten 1,000 wave numbers for A and 4,000 wave numbers for B. All right, so this is how our IR spectrum looks, right? So we have our wavelength here, and you might not necessarily see the wavelength. Microns is equal to 10 to the minus 6 meter, which, we just looked at the conversion factor. But what you will most definitely see is the wave numbers here on the x-axis, right? And there's a direct correlation between our wave number and our frequency, which we just mentioned. And then on our y-axis, we have transmittance, and you'll see percentage T, right? So this is how our spectrum looks, and we have peaks representing different functional groups. So for example, so we need to know our functional groups, and we're going to, this is just, a premature look at a spectrum because we haven't gone into all of the details yet. But we need to know our functional group. So we have, for example, our carbonyl here, we have our aromatic group, we have our hydroxyl, and we have our methoxy, right? So once we look at a spectrum, we don't have to necessarily know the exact wave numbers, but we need to know our functional group and know that they correlate with a particular wave number within a particular range, right? So this is what the spectrum looks like. So we would want to look for a peak for the carbonyl. We might see a couple peaks for the aromatic. We would want to look for a peak for the hydroxyl and for the methoxy here. All right, so this is another example here. This is ethanol, right? And I like this animation because it tells you which peak corresponds to which functional group, right? So here we know the structure of ethanol, do we? So that CH3, CH2, OH, right? And so we can see here that the functional group, so the first one is the hydroxyl, the second one is, represents all the CH functional groups, and then the third one would be the CO portion, right? So that region here. So each of these correspond to a particular wave number, and as we said, we need to know our functional group and know what aligns with what, right? So this is a fun example. All right, so a fun fact here. Bond strength and wave numbers. So for organic compounds, absorption energy is roughly parallel bond strength, right? So here we have triple bonds, double bonds, and single bonds, and there seems to be some correlation between the strength of the bond and the absorption energies. So we're seeing here in the 2000 regions for the triple bond, in the 1500 to 1900 region for the double bond, and lower numbers for the single bond. So we can, get an estimation of, a type or strength of a bond by virtue of their absorption energies. And these are for organic compounds. So notice that we have carbon in all of these. All right, so let's take a second to look at the fundamentals of obtaining spectra. So an IR radiation is passed through a sample, and I need you now to use your imagination somewhat, right? So the IR radiation is passed through the sample. Some of the IR radiation is absorbed by the sample and some of it is transmitted. So I don't know if you guys recall here, right? When we're looking at percentage transmittance, sorry, right? So that is why we're seeing here that some of the IR radiation is absorbed and some is transmitted. Transmitted radiation is detected, and a plot of transmittance versus wave number is produced, as we saw on the spectrum. So, just to mention the older dispersive spectrophotometers, right? So, this is how, in the past, and history is always good. It's always good to know where we're coming from to have a better appreciation of where we are now, right? So, in these older spectrophotometers, we had the source, the Nernst glow, a molded rod made of a mixture of oxides, various oxides, which is surrounded by nichrome wire and heated electrically to 1500 degrees Celsius. A beam split by mirrors into two beams, one passing through the sample and the other through the reference, which is usually a solvent. The sample beam and the reference beam pass through a monochromator, which enables variation of the specific IR frequency reaching the thermocouple detector. The detector can sense the ratio of the intensities of the reference and the sample beams. The signal from the detector is amplified, and a recorder draws a spectrum of the sample on a chart. So, samples must be placed in containers or matrices which are transparent to IR. So, back then, the IR transparent materials like sodium chloride or KBr, potassium bromide, IR data may be collected on compounds. So in the vapor phase, gas cells as liquids film between sodium chloride plates in solution, so using solvents like chloroform. In the solid state, using KBr pellets, etc., right? So this is how it was done previously. It was indeed a lot of work. However, developments in computing technology, optics, instrumentation have led to widespread availability of FTIR, and that is Fourier transform IR spectrophotometers, and all the dispersive instruments are now almost obsolete, and perhaps at this point they are. FTIR spectrophotometry is based on the production of interferograms, right? So bear in mind here that we just want to have a general understanding of the instrumentation that we use to produce this spectrum, right? We just want a general idea. So we're not going to go in depth into the Fourier transformation or interferograms and those types of things. So this is us trying to have a general understanding, right? So this is an image here of the setup, right? So I'm going to walk through it slowly. So let's consider light of a single wavelength in the IR range. The light is split by a beam splitter here, right? So this is a single frequency source here, and we have a beam splitter here. So the light is split by a beam splitter into two beams. The first one is a fixed mirror and a moving mirror. So let's see the fixed mirror here, and we have the movable mirror here. So one beam is reflected by a fixed mirror, then reflected partially back to the source and partially to the detector. Where is the detector? Down here. The second beam is reflected by a moving mirror, which is here, then reflected partially back to the source. Here, this is the source, and partially to the detector as well. The energy that reaches the detector is the sum of the two beams. The beams can reinforce or cancel each other depending on the distance moved by the movable mirror. So here, or movable mirror here. So it could not move, or it could move by, different wavelengths here. The resulting signal is known as the interferogram. So this is our interferogram here that results, and has an infinitely long cosine wave. In the FTIR, the single frequency source in the schematic is replaced by a heated element or glower containing electromagnetic radiation in the entire IR range. The sample is placed in the beam before the detector. So here we see the sample before the detector. The interferogram is highly complex, and as we said, we're not going into that, and contains all the IR frequencies and their intensities transmitted by the sample. An IR spectrum is generated by subjecting an interferogram to Fourier transformation. So having said all of that, let's see if you can, have an animation to kind of show what happens. So we have the light coming from the source, and this is a beam splitter. Remember, it splits it up into the moving mirror and the fixed or static mirror, right? So notice the direction of the flow, the arrow. It comes back partially, right? And then it goes through the sample and to the photodetector, where the interferogram is produced and Fourier transformed, right? So this is basically what I was saying in a couple seconds. So hopefully that would have added some more clarity. So experimentally, an interferogram of the background or instrument chamber is acquired and a spectrum is generated and stored. The sample is introduced. No sample preparation is necessary. So I don't know if you recall when we're talking about the whole sample, it has to be dissolved or mixed with KBr, sodium chloride, for example. In this case, in the newer spectrophotometers, no sample preparation is necessary for solids and liquids. A small quantity of the sample is placed on a crystal of diamond and, various things, but it's very hard. The interferogram and spectrum of the sample is obtained, and the spectrum of the background is subtracted from the spectrum of the sample. The entire operation takes about 2 to 3 minutes, literally, right? So that's basically it. As we said, we're trying to have a general understanding of how the instrument works. So an IR spectrum chart showed, we saw downward peaks, and we saw the percentage transmittance on the y-axis, and we saw the wave number on the x-axis. What I want to introduce here is peak intensity is qualitatively described, right? So we will describe the peak as either strong, and you might just see S. When you look at the IR data tables, you might not see the word strong, medium, weak, or variable, but you might just see the letter S, M, W, or V, right? So what that means is that the peak is either strong, medium, or weak, right? Relatively speaking. So as we said, it's qualitative. Application and correlations. So, application of IR spectroscopy to structure elucidation of organic compounds is largely an empirical process. So, what structure elucidation means, and that's kind of what we'll be doing for this semester. We apply IR spectroscopy to figure out the structure of compounds. So, if we're starting off with an unknown compound, right? We're trying to figure out what the structure is. We call that structure elucidation. And IR is used, very heavily used in that area. So once material of sufficient homogeneity is obtained, example from a synthetic transformation, the IR spectrum is determined. IR absorptions or lack thereof indicate the presence or absence of functional groups. Negative evidence is just as important as positive evidence. And this is important because when you look at a spectrum, it's not only important to say, what is there, it's also important to say what is not there, right? Negative evidence is just as important as positive evidence because that will rule out certain things. So now we're going to talk about IR spectroscopy application. All right, so let's see if we can, at some point go into some applications. All right, so, and, we're going to talk a little bit, mention a little bit more about, how we use it. And to do that, we have to mention, give some background information. And notice here that we have spoken about some of these things before. So sometimes, we're trying to reinforce and strengthen certain concepts by repetition. So IR, it can be very sensitive to determination of functional groups within a sample, since different functional groups absorbs different particular frequency in IR radiation. Also, each molecule has a characteristic spectrum, often referred to as the fingerprint, right? So we looked at the spectrum for, what was it, vanillin? Right, vanillin. So this spectrum would be considered a fingerprint for vanillin. So in the future, if you have a sample and you're not certain what it is, you can just run an IR of it. And if it looks exactly the same as, what is published, what is recorded, then we can basically use it as one method to clarify that. A molecule can be identified by comparing its absorption P to a data bank of spectra, which is what I just said. The IR spectroscopy is very useful in the identification and structure analysis of a variety of substances, including both organic and inorganic compounds. It can also be used for both qualitative, so we just saw qualitative by, looking at the spectrum, and quantitative, which we haven't looked at, analysis of complex mixtures of similar compounds. So it can be qualitative, which we have seen, and it can also be quantitative, which we haven't looked at yet. Criterion for IR absorption is a net change in dipole moment in a molecule as it vibrates or rotates, right? So I mentioned the dipole moment earlier, so now we're going to go into it a little bit more. Using the molecule HBr as an example, the charge distribution between hydrogen and bromine is not evenly distributed. Since bromine is a more electronegative element than hydrogen and has a higher electron density, right? And so HBr has a large dipole moment and is therefore polar. The dipole moment is determined by the magnitude of the charge difference and the distance between the two centers of charge. So as the molecule vibrates, there is fluctuation in its dipole moment. This causes a field that interacts with electric field associated with radiation. If there is a match in the frequency of the radiation and the natural vibration of the molecule, absorption occurs, and this alters the amplitude of the molecular vibration. So we saw this in the video and we mentioned this already, right? We're not even adding anything new here. We're just reinforcing the point that for a molecule to absorb IR, it needs to be polar, essentially. That's what we're seeing here. So having said that, now we have a question here. The following molecules cannot absorb IR radiation. Why? So we have oxygen, nitrogen, and bromine. So take a second, think about it, and all right, let's see if you know already. They do not have a change in dipole moment, amplitude, nor orientation. When they undergo rotational and vibrational motions, as a result, they cannot absorb IR radiation. So they don't have a change in dipole moment. Let's look at polyatomic molecular vibration. So molecular vibrations consist of stretching and bending modes, as we saw, right? A molecule consisting of n number of atoms has a total of 3n degrees of freedom. In a non-linear molecule, 3 of these degrees of freedom are rotational and 3 are translational, and the remainder is fundamental vibration. So I hope you remember, we mentioned 3n minus 5, 3n minus 6 already. So now we're diving a little bit deeper into that. In linear molecule, there are 3 translational degrees of freedom and 2 are rotational. So 3 translational degrees of freedom and 2 are rotational. This is because in a linear molecule, all the atoms lie in a single straight line, and hence a rotation about the bond axis is not possible. So for linear molecules, for vibration, we therefore have 3n minus 5 modes. And for nonlinear, as we saw previously, 3n minus 6 modes, right? So let me just repeat it. For a molecule consisting of n atoms, it has 3n degrees of freedom. That's for the atoms, right? For a molecule consisting of n atoms, right? And what we're seeing here is that some of the modes are rotational, some are translational, and some are vibrational, right? So these are, when we talk about 3n degrees of freedom, we're talking about rotating, translation, and vibration as degrees of freedom of a molecule. 5 is subtracted from linear molecules because 3 represents translational degrees of freedom and 2 rotational. So what we're saying is that the rest must be vibrational, right? For a nonlinear molecule, we're saying that 3 of these is rotational, 3 is translational, and that is 6, right? So if we subtract, our total 3n degrees of freedom, we subtract 6 from it, then the rest of it must represent the vibrations, the vibrational modes of freedom. I hope that is clear. So let's look at example number 1, water. So water is a nonlinear molecule, and we're going to go through this quickly because this was in the video and I spoke about this already. Water is a nonlinear molecule due to the uneven distribution of the electron density. Oxygen is more electronegative than hydrogen and carries a negative charge, while hydrogen has a partial positive charge. The total modes of vibration for water will be 3 times 3 minus 6, right? So we did that calculation already. 9 minus 6 equal to 3 modes, which correspond to the stretching and bending vibrations. All right, so taking this video.
Example, here we're going to take a look at a water molecule, and below it is just a sample IR spectrum of water. And water has these different places where it absorbs IR energy to give these different vibrational modes. So the first one here we'll look at 3727, we can see we have this stretch between the oxygen and hydrogen, and this in fact is an asymmetric OH stretch. Then if we move on to 3607, it's another type of OH stretch, but this is a symmetric OH stretch. So another place where this molecule absorbs IR energy. And then finally down here at 1640, we have a bending. So HOH bending, and this is an in-plane bend.
All right, so I hope if I ask you what kind of in-plane bend, you can answer that. All right, so let's look at example number 2, carbon dioxide. So carbon dioxide is a linear molecule, unlike water, and thus has the formula 3n minus 5. It has 4 modes of vibration. If we do the calculation, 3 times 3 would give us 9, minus 5 gives us 4. 2 of those are stretching modes, so symmetric and asymmetric. However, the symmetric stretch is not IR active because there's no change in dipole moment. The net dipole moments are in opposite direction, and as a result they cancel each other. In the asymmetric stretch, oxygen atom moves away from the carbon atom, which generates that net change in dipole moment and hence absorbs IR radiation at 2350 wave numbers. The 2 bending modes are degenerate or equal in energy. Right, so we have 4 for carbon dioxide. One is IR active. Well, for the 2 stretching modes, one is IR active and one is not. For the 2 bends, they're degenerate. They're equal in energy. So here we see, this animation with the vibrational modes of carbon dioxide. So we're seeing the asymmetric stretch. So let's look at it again. So we said the symmetric stretch is not IR active. So what we're seeing here is the asymmetric stretch, right? And the bending vibration. So we're seeing the bending vibration. I hope you're noticing there that we have absorbance here and the movement correlates with this being um look at the difference. So the action links to a particular peak. And I know that we're not used to seeing an IR spectrum like this. But it just for instructional purposes to see the stretching and the bending vibrations. As we said, the two we're just seeing one peak for the bending because both of them have the same energy. All right, so we're seeing the asymmetric stretch. We're not seeing the symmetric stretch because, as we said, it's not IR active. And we're seeing, well, for the bending, it has both twisting and wagging, right? So both of them, we're not seeing both of them on the animation, but both of them would occur at the same energy because they are degenerate. That's for the bending. All right, so moving right along. For we use IR for, in this case, qualitative analysis, identification of functional groups. So formaldehyde has a carbon double bonded to an oxygen functional group, which we call a carbonyl, and it has a CH bond, right? So this is the structure of formaldehyde. Sorry. So we have a carbon in the middle, and we have a carbonyl here, and we have two CHs. A molecule with a carbonyl stretch has an IR band, which is usually found near 1700 wave numbers and around 1400 wave numbers for the CH2 band. The higher wave numbers indicate a large dipole moment change. It is easier to bend a molecule than to stretch it. Hence, stretching vibrations have higher frequencies and require higher energies than bending modes, right? So I'm sure we probably would have picked that up for even or carbon dioxide here, and even for water, where we saw the stretching vibrations having higher frequency and requiring therefore higher energy than bending modes. So IR analysis is also used quantitatively, and I suppose less so. For the quantitative analysis is not as accurate as other analytical methods like GC, gas chromatography, or liquid chromatography. The main theory of IR quantification is Beer-Lambert's law. So you may have been introduced to this equation before, where A represents the absorbance of the sample, I represents the intensity of the transmitted light, and the I naught is the intensity of incident light, L is the path length here, epsilon is the molar absorptivity of the substance, and C is the concentration of the substance. So as we know with the Beer-Lambert's law, we see a relation between the absorbance and the concentration of the sample. So as I said, it's less IR is used less frequently quantitatively. It's more so used qualitatively, as we saw with the formaldehyde, to identify the presence or absence of functional groups. So what are the factors which influence IR? Well, Isotope effects. When an atom is replaced by an isotope, it has an effect on frequency due to changes in the new mass. This is because the new mass has an effect on rotational and vibrational behavior. Solvent effects. Well, the polarity of the solvent will have an effect on the IR spectra due to interactions between solvent and compound. So you would therefore see that you will um, perhaps quote the solvent. So when you're reporting IR data, you will definitely um, quote the solvent, right? Because the solvent would interact with the IR or influence the IR. So you generally report the solvent if you have used solvent along with the data. So what are some of the advantages of IR? Well, high scan speed. As I said, within minutes you can get your data. So IR spectroscopy can get information for the whole range of the frequencies simultaneously within 1 second. Therefore, IR can be used to analyze a substance that is not very stable and finish the scan before it starts to decompose. So that's a very good advantage. High sensitivity. So with Fourier transform, which is a newer method, the IR spectrometer does not need to use the slits and monochromator as we saw. In this way, the loss of energy in the analysis process will be decreased. Therefore, the energy that reaches its detector is large enough, and even very small amount of analyze could be detected. So we're talking even, well, I've used, milligram quantities, so it's very sensitive. Another advantage is the wide range of applications. So IR spectroscopy could be used to analyze almost all organic compounds and some inorganic compounds. It has a wide application in both qualitative analysis and quantitative analysis. As we saw, the sample could be gas, liquid, or solid, so that's nice as well. Large amount of information. So IR spectra could give us lots of structural information of the analyte, such as the type of bond, the functional group of the bond, the stereoscopic structure of the compound, even though we haven't looked at that, the number and position of substituent group, and so on. Depending on the available information for the functional part and the fingerprint part, IR spectroscopy has become a great method to identify different kinds of compounds. And then finally, it's non-destructive. Our spectroscopy is non-destructive to the sample, and that is very important. Even me as a natural products chemist, when you have milligram quantities, very small quantities, and you want to get the data, you can get the data and use a sample for other spectroscopic methods. So it's that's a very, well, all of these advantages are important, but this one is very important. All right, so what are some of the disadvantages? Well, sample constraint. IR spectroscopy is not applicable to the sample that contains water, since this solvent strongly absorbs IR light, as we have seen several times. So if you want to run a sample in water, you might have an issue. Spectrum complication. The IR spectrum is very complicated, and the interpretation depends on a lot of experience. Sometimes we cannot definitely clarify the structure of the compound just based on one spectrum. So we have to complement it with other spectroscopic methods such as mass spec or NMR in order to further interpret the spectrum. To further elucidate the structure, to figure out the compound. We cannot just use IR. right? We have to combine it with other methods in order to figure out the structure. And quantification. Well, IR spectroscopy works well for qualitative analysis of a large variety of samples, but quantitative analysis may be limited under certain conditions, such as very high or very low concentrations. So we mentioned that disadvantage already. And environmental application, well, molecules of carbon dioxide can absorb energy from IR radiation. As we have seen, the energy from photon causes the carbon dioxide molecule to vibrate, as we have also seen. The molecule then gives up this extra energy by emitting another IR photon. So once the extra energy has been removed by the emitted photon, the carbon dioxide molecule stops vibrating. The carbon dioxide molecule may also transfer the energy gained from the absorbed photon to another molecule, adding speed to that molecule's motion. The faster motion of the molecule raises the temperature of the gases in the atmosphere. So, this ability to absorb and re emit IR energy is what makes carbon dioxide an effective heat trapping greenhouse gas. And so, carbon dioxide molecules can vibrate in ways that simpler nitrogen and oxygen molecules cannot, which allows carbon dioxide molecules to capture the IR photons. And so, we can explain the whole global warming effect. Greenhouse gases and the greenhouse effect play an important role in the Earth's climate. In recent years, however, excess emissions of carbon dioxide and other greenhouse gases from human activities, mostly burning fossil fuels, have begun to warm Earth's climate at a problematic rate. Other significant greenhouse gases include water vapor, methane, nitrous oxide, and ozone, right? So we're seeing here the environmental application of IR. So having that knowledge and understanding of how molecules absorb IR radiation has impacted the field of the environmental chemistry in this way. All right, so finally, I'm not going to spend any time on this, but the idea here is that IR tables, you can, download IR tables, you can look at them. This is what they look like. You will see the functional group, whether or not it's a stretch or a bend or both. You will see the wave numbers. So you will see the functional group, whether or not it's a stretch or a bend. You will see the wave numbers, and you will see whether or not it's a strong, medium, or variable peak, right? So this is not something that you have to try to remember. Well, I would advise you to remember the common ones, like alcohol, carbon dioxide, not carbon dioxide, the common functional groups, right? Carbonyl, for example, and hydroxyl comes to mind, right? But it generally, this is not information that you store, right? We generally have a table and that you can use as a reference. But as I said, I would encourage you to know the common ones. All right, so just skipping through the information on the tables. So again, you will see the functional groups. You will see whether or not stretch or bend. You will see the wave numbers, and you will see whether or not strong, medium, or variable, right? And then finally, we have our question, which we will answer in class. Unknown molecule with molecular formula C5H10O. Which of these five molecules it is most likely to be? Is it most likely to be? All right, so you analyze the spectrum, right? So you're going to need your table, right? And you're going to need your table and you're going to need your molecular formula to look for the peaks, right? So you're going to look at the functional groups of the various compounds and see whether or not which one matches, which one does not to this spectrum here. So we'll answer this one in class. So if you have made it to this point, thank you so much for watching and see you next time.